Our homework last night that we needed to finish up for homework was worksheet number 7, and we had 2 requests to go over questions 3 and 4. Question 3 relates back to question 1B, except in this one, we're going to move the third charge below the second charge. In question 1B, it looks something like this. In question 3, it looks something like this instead. Here's charge 1, here's charge 2, and here's charge 3. And if we go back to that page that had question 1B on it, we would see that the charge on number 1 was 5 times 10 to the negative 5 coulombs. Charge on number 2 was also 5 times 10 to the negative 5 coulombs. And the charge on number 3 was negative 2.5 times 10 to the negative 5 coulombs. There was also some distances given to us in question number 1B, 2.5 centimeters and 2.0 centimeters. Although we got to make sure that we convert that centimeters to meters because we always have to be in the standard units. Now, if you did question 1B, where all 3 of those charges were in a row, then we would have drawn a free body diagram, force to the right, force, another force to the right, would have looked something like this, would have calculated both of those forces, added them up both as positive values, and been done. Here, we still have to start off by drawing a free body diagram. But what we do with that free body diagram ends up being a little bit different here. Charge 1 and 2 are both positive. That means they're going to do what to each other? Attract or repel? They're going to repel each other, right? That means charge number 2 is going to be pushed away from charge number 1. Now, 1 would be pushed away from charge 2 because it's an equal and opposite repulsive force. But we're not looking for what happens to number 1. We're looking for what happens to number 2. Let's look at charge 3 on number 2 now. That's an attractive force because 1's positive, 1's negative. That means number 3 will pull 2 towards it. And 3 will be pulled towards number 2, but that's not the question, so we don't really care about that right now. We get the values of both of those forces, F12 and F32, both by Coulomb's law. KQ1, Q2 over R squared. I'm going to write in the number for this. If you're having trouble getting this number, let me know so I can show a little bit more work, okay? When I do that work, I get a value of 3.596 times 10 to the 4 newtons. You guys okay with that? Devin, is that okay, that number? Okay, make sure, the one big thing you got to make sure of is that you make the distance 0.025 meters, and then you got to square that distance. If you do that, you should get 3.596 times 10 to the 4. F32, similar type thing here, KQ2, Q3 over R squared. This time different charges. This time our distance will be 0.02 squared. And when we do that math, we get 2.8094 times 10 to the 4 newtons. Now, here's the crux of it. We got to add these forces together, but it's not good enough this time to just say 3.59 plus 2.8 equals whatever. We have to add them vectorially because they're in different directions. So how do we do that? How do we do that? Vlad? We don't really have an angle there, right? 90 degrees, right? Help them out there? Yeah, yeah. If we've got a funny angle, then we've got to get rid of the funny angle and turn it into X and Y. But Kenton, you're right. We already have X and Y here. We don't need to get rid of any funny angle and turn it into X and Y. We already have it. So we've got F12 to the right. Its value is 3.596 times 10 to the 4. We've got F32 downwards. That's 2.8094 times 10 to the 4. And we're going to find our resultant vector right there, our force right there. When we do that math, Devin, how are we going to find that force? When we do the math to find force, what are we going to do exactly? Pythagorean theorem, good. So 3.5 squared, 2.8 squared, square root that, and we should get that force, do that math, of 4.56 times 10 to the 4 newtons. We're going to find that angle by using the inverse tan function of opposite over adjacent. Do that one, we get 38.0 degrees. We got a real similar thing we have to do with number 4. except this time we're repeating 2b instead of 1b. The diagram for number 4 is going to look like this. Here's charge 1. Is a charge, if we go back to the data on question 2b, 2.5 times 10 to the negative 2 coulombs. Charge 2 is negative 4.0 times 10 to the negative 2 coulombs. And charge 3 over here is 3.0 times 10 to the negative 2 coulombs. Oh boy, they're really nasty on this one, or I'm really nasty on this one, I guess. 60 millimeters and 5 centimeters. Boy, how easy would it be to make a mistake on those? 2 different non-standard units. The first one, millimeters, how do you get that to meters? Millimeters to meters. Josh? Okay, you can divide by 10 to get centimeters, and then divide by 100 to get meters, sure. Or you could just divide by 1,000 and get meters right off the top. It doesn't make any difference. Okay? If it's easier for you to go from centimeters to meters, then convert to centimeters first. That's fine. Okay, it's 2 steps. Okay, it's going to take you about 1 second or 2 seconds extra. That's it. Centimeters to meters is divide by 100. So divide by 1,000, divide by 100, or convert to centimeters and then divide by 100. All right, let's do our free body diagram here. 1 and 2, opposite signs. Because they're opposite signs, they're going to attract or repel. Opposite signs are going to attract, right? If they're going to attract each other, then 2 will be pulled upwards towards number 1. We'll call that F12. 1's going to be pulled downwards, but we don't care. John, 2 and 3 are negatively charged. They're going to attract as well, right? Is 2 going to be pulled towards number 3 or pushed away from it? Good. We're going to call that F32. Now let's go through the same process as we just went through. Let's say F12 is K Q1 Q2 over R squared. We do the math there, but be careful because our distance is 0.06 squared. It's 60 divided by 1,000. When we do that math, we should get 2.4972 times 10 to the 9 newtons. And the force of 3 on 2, same deal here, except our conversion's a little bit different. We're dividing by 100 this time. It works out to be 4.3152 times 10 to the 9. And finally, Andy, what am I going to do to add these numbers together? Yeah, we'll do the Pythagorean theorem, but in order to do the Pythagorean theorem, we need a right-angled triangle. So let's draw that right-angled triangle. We have a force this way, we have a force this way. The first one is 2.4972 times 10 to the 9 newtons, and then the second one is 4.3152 times 10 to the 9 newtons. And then, of course, we're going to find force there by the Pythagorean theorem. And we're going to find theta by the inverse tan function of opposite over adjacent. So we get force there, 4.99 times 10 to the 9 newtons. And we get our angle, the inverse tan function of this over this gives us 30.1 degrees. If you haven't finished these check and reflect questions, which we gave you yesterday, but didn't assign for formal homework. If you haven't finished those, I'm going to ask you to finish those up for formal homework here tonight. We're going to skip forward a little bit here now. Stop talking about forces per se. Start talking about fields. If you remember back in Physics 20, we talked about another kind of field. It was a gravitational field. We defined a field in general as a line of influence that surrounds something. Specifically, a gravitational field was a line of influence that surrounds an object with mass. The Earth produces a gravitational field because it has mass. The sun produces a gravitational field because it has mass. You produce a gravitational field because you have mass, albeit a very small mass, and therefore a very small gravitational field. Things with mass cause gravitational fields. Things with mass influence other things. Now, things with charge also influence other things. Therefore, things with charge will also produce a field. But this time, it's not going to be a gravitational field. It's going to be an electric field. Masses cause gravitational fields. Charges cause electric fields. Now, of course, we'll go back to gravitational fields for a moment here. Take a big rock, put it in a gravitational field. It's influenced by the gravitational field, but it's influenced in a very particular direction as well. If I put the rock in the gravitational field surrounding the Earth, then the rock will fall down toward the Earth. You will fall down toward the Earth because gravity pulls down. The gravitational field has a direction associated with it. Rocks don't fall up. Rocks don't fall in random directions. Rocks fall down because gravitational field has that downward direction associated with it. A gravity field is a vector field. Similarly, an electric field also influences things, not just influences things in random directions, but in a particular direction. An electric field is also a vector field. It also has a direction associated with it, as opposed to something like a light field or a heat field. Light influences us, heat influences us, but not in a particular direction. So something like a light field or a heat field or something like that would be good examples of scalar fields. Things that influence, but things that influence in no particular direction. Now, again, let's go back to gravity for a second, because that's the one that we can see, right? That's the one that we've had experience with in Physics 20, but it's also the one that we can visualize a little bit better because we experience gravity a little bit more often than we experience electricity. A gravitational field is caused by a mass, like the Earth, for instance. The gravitational field caused by the Earth is there as long as the Earth is there. Right now, you experience that field. But if you were to walk out this door, or you were to go to another planet, you would no longer experience the field that's inside this room, but the field would still be here. The field is here whether you're here to experience it or not. I'm sorry, the world doesn't revolve around you. If you're gone, the gravitational field is still there. It's there as long as there's a producer there to cause it, to produce the field. A force, on the other hand, isn't there unless there's something there to experience it. The force of gravity that you experience is your weight. If you disappear, you go to another planet, then you don't have a weight. You don't have a force of gravity. There's still a field caused by the Earth, but there's no force if there's nothing there to experience it. Now, we can make that translation to electricity as well. Electric charges produce electric fields. And those fields are there as long as the producer is there. As long as they don't cause the charge, or as long as they don't take away the charge that's causing the field will still be there. Now, there may be an experiencer. If there is, then there's going to be a field and a force. But if you don't have an experiencer, or if you take the experiencer away, the field's not going to disappear, but the force will. How did you define force in Science 6 and in Physics 20? Force is defined 3 words. Push or pull. That's it. If you don't have a push, if you don't have anything to push and you don't have anything to pull, then you can't have a force. You can't have a push if there's nothing to push. You can try to push all you want. If there's nothing to push, there's no push. In order to have a push, you need something to experience the push. You need a force. In order to have a force, you need something to experience the force. But, hey, you're trying to push something, you're still there. Okay, the producer is still there, even if there is nothing to push, even if there's not an experiencer. Now, let's define the direction of the field. Just like gravity has a direction, right? It's a vector field. The gravitational field, because it's caused by mass, and because there's only one kind of mass, it's easy. The gravitational field is always toward the producer. It's always the direction that an object would move if placed in that field. Put this pen in the gravitational field, drop it, it's going to fall downward toward the Earth. In other words, the gravitational field points toward whatever produces the field. But it's simple because there's one kind of mass. With charge, there's two kinds. So the field can look a little bit different depending upon what kind of producer you have. We're going to arbitrarily define the electric field. By arbitrarily, I mean somebody sometime just decided this. There's no good reason for it. It's just the way it is. We're going to arbitrarily define the direction of the electric field as the way that a positive particle would move if placed in a field. For instance, here's a positive producer right here. Here's the shape of the field that surrounds that positive producer. If I was to put a positive charge in that field, which way would it go? Now, I'm not saying I need to put it there, but if I was to put it there, which way would it go? Away from it. So the electric field goes away from the producer. Away from this producer, at least. Let's make another producer. This one's negative. Shape looks exactly the same. Direction, maybe not. If I was to put a positive producer here, where would it go? And here it went away. Here it goes towards, right? It's attracted towards it. So we're going to say the electric field surrounding the negative is towards it. It's the way that a positive particle would move if it was placed in the field. And it's also away from a positive toward a negative. I got a question for you. What if I took away that positive? Would that change the field? No, why not? Yeah. The field is still there even if the particle's not. Good. The field, yeah, go ahead. Nothing to influence it. Okay. In the end here, the field was caused by the producer. The producer is what affects the direction. If you take away the charge, the direction is still the same. The field's still there. There's no force, but there's still a field in the same direction. Remember what the definition said. It doesn't say the way that a positive moves in the field. It says the way that a positive would move if it was in the field. So there's still a field away from the positive toward the negative, because if I put a positive in that field, that's the way it would go. I don't need to put the positive there. If I did put it there, that's the way it would go. Here's another one for you. What if I put a negative right there? Which way would it go? Kevin, if I put a negative there in that field, which way would it go? It would go away. Good. Does that mean we have to change the direction of the field? The field is independent of what experiences it. The field is still towards it. Positives move with the field and negatives move against the field, opposite to the field. What if I do this? Here's a tough one for you. What if I drew an electric field that looked like this to the right? And what if I put a positive particle in that field? What caused that field? I don't know. Was it something over here, or something over here, or both? I don't know. Okay, we know nothing about what caused the field here, but it was caused by something. If I put a positive particle in that field, which way is it going to go? To the right. Because the field was defined as the way that that positive would move if it was placed in that field. What if I took that away and I put a negative in there? Which way is the negative going to go? No. The negative would go, anyone? Not to the right, to the left. How do you know that? We don't even know what caused that field. It doesn't matter. Positives move with the field, negatives move against. Maybe this was caused by a big positive charge over here. Well, if that's the case, then the negative is attracted to it. Maybe it was caused by a big negative over here. Well, it doesn't matter. If it was, then the negative is repelled by it. So if the field is to the right, a negative particle moves to the left, a positive moves to the right. That make sense? Take a look at a couple diagrams here. First one's positive. Field looks like this. Second one's negative. Field looks like the same, if we're just drawing the shape here. What about directions? First one, toward or away? Devin, towards it or away from it? Good. I didn't put a positive particle in that field, but if I did, it would be repelled by the producer, so it's going to go away from it. Negative would go opposite to that. What about the second one? Kyle, what about the second diagram there, the negative producer? Which way is the field going to point there? Inwards, towards it. Good. I didn't put a positive particle in that field, but if I did, Kyle, it would move towards it. It'd be attracted towards it. So the field is arbitrarily defined as toward the negative producer. Let's draw another one. This time you got a positive and negative. That are pretty close to each other. And you can see that the field lines still look the same. But this time we're going to put them close enough together so that they may actually interact with each other. If that's the case, then all we're going to do is join the field lines together, and it's going to look something like this. The field lines leave the positive, they go toward the negative. Hey, what if I put a positive particle right there? Where would it go? Where would it go? There's the million-dollar question. Josh thinks he knows it. Toward the negative, like that? Oh, say it again. Through the path, like through here? Yes. It would follow exactly that path. It has to. Right? It has to. Let's go back to the definition. The direction of the field is the direction that a positive particle would move if placed in the field. So if that's the direction of the field, that's got to be the direction that a positive particle would move if placed in the field. Positives follow the field. Negatives, hey, Josh, if I put a negative right there, it's going to go this way, right? Opposite to the direction of the field, but still along the same path. Let's draw one more diagram. This time, we've got a positive and a positive producer. Draw a bunch of field lines surrounding both of them. What are they going to do? Well, when they hit each other, when they encounter each other, they're not going to join up like they did in the last one because they repel each other. So this field line right here is going to be repelled by this guy. It's going to go up something like this. There's actually a point in between those two positive charges, right in here, where there is no field. It's completely canceled out. The field strength there is 0. And that's why midway between these two charges, there wouldn't be a force. If I put a charge in that spot where the X is, there wouldn't be a force on that charge because there's no field. Basically what we're saying is it's attracted to both of them or repelled by both of them. The forces would cancel, no force. Here's 3 equations that you learned last year for gravity. First one is for gravitational force, right? Well, let's look at the equivalent for electric force. We did this last week, so this shouldn't be new to us. The gravitational force is gm1 m2 over r squared. The electric force is k q1 q2 over r squared. Look a lot the same basic structure, right? They're both inverse square relationships. We get a different constant. We're not using mass anymore, we're using charge, but they look a lot the same. The second equation that you see here for gravity is for the gravitational field strength. It's the field strength caused by something, or the field strength surrounding a producer. Anybody want to take a stab at what the electric field equivalent would be to that? Yep. Good. Easy to go to KQ over R squared. We're going to use that to find the electric field if we have information about the producer, what caused the field. And then the last equation, of course, is also for electric field. But this is the electric field that's experienced by something, the experiencer equation. The field caused by the Earth is 9.81. The field experienced by you is 9.81. If we have information about the Earth, we'd use this equation, the producer equation. If we have information about you, the experiencer, we'd use this equation. The electric field is equal to what? You know this. You've never seen this equation before, but you know this. Mason, what do you think it is? Nope. Nope. Yep. F over Q. Right, if gravitational field was F over M, then the electric field is F over Q. I want to look at 2 things before I take a look at an example, a couple example problems here. Number 1, notice for electric field, there's always a vector sign over it. It looks a lot like energy, right? E, capital E, that's the symbol for energy. But there's a vector sign over this because it's a vector field. Now, sometimes we put absolute value signs around it, sometimes we don't. We're not going to lose any sleep over that. But I want you, 100% for sure, to put the vector sign over it. Here's why. Every single person in this class will mix up energy and electric field at some point if you don't put the vector sign over it. I promise you, everybody will. Okay, you think you're smart? You know what? You are. But you're still going to mix them up. Now, you might mix them up on a homework question when it doesn't really matter, or a quiz when it doesn't really matter, or a unit test where it matters a little bit more, or a diploma exam where it matters a lot. You will mix them up if you don't put the vector sign over it. You may not think you will, okay, but you will. Put the vector sign over it, because you know what? You might still mix them up, but you're a lot less likely to mix them up if you put the vector sign over it than if you don't. Put the vector sign over it. Second thing is, let's look at the units here. What do you think the units for electric field would be? Look at this one. Josh? Newtons over coulombs. Hey, let's take a look at this one. K is Newton meter squared per coulomb squared. Okay, Q is coulombs over meter squared. Well, that looks ugly, but if we start canceling things, what are we left with? Newtons per coulomb. Just like newtons per kilogram were the units for gravitational field, newtons per coulomb are the units for electric field. Okay, here's a question. It says a sphere with a negative charge of 2.1 times 10 negative 6 coulombs, negative charge, experiences a force of repulsion of this value when it's placed in an electric field produced by a source charge. Okay, there's a diagram in the book, but I purposely didn't put the diagram in here because I think you guys can do this without the diagram. Draw your own. What's the field source charge produced at that sphere? So let's draw this. We've got a negative charge that experiences a force of 5.6 times 10 to the negative 2 newtons. We've got a producer over here that caused that field. Okay, we want to find the field strength caused by this producer at this point. If you just read the last sentence of this question, then you're going to think you're going to use the producer equation, right? Because you're trying to find the field strength produced by it. But we know nothing about the producer. So let's use the experiencer over here. Let's say E is equal to F over Q. Get the field experienced by the charge, by the experiencer. I get 2.48 times 10 to the 4. Look, if that's the field that's experienced by this guy, what caused it? What caused it? The producer. So what's the field that's caused by the producer? 2.48 times 10 to the 4. Think of it this way. What gravitational field do you experience right now? What's the value of the gravitational field that you experience right now? Colin, you got that? What's the gravitational field that you experience right now? It's not a trick question. What? Sorry? How about just 9.81? Yeah. Gravitational field that you experience is 9.81. What's the field produced by the Earth where you are sitting right now? 9.81. Why? Well, because you experience a field. It has to be caused by something. This guy experiences a field of 2.48. It has to be caused by something. The field produced by this guy is the same as the field experienced by this guy. So even though we were looking for the field produced, we didn't have any information about the producer. We used the experiencer data to solve for the field. All right. Here's a couple questions to work on for the next few minutes. One more question for us to work on here now is the example question. This one says, determine the electric field at a position P that's this far away from the center of a negative point charge of this value. So let's see here. We have a negative point source. It's negative 1.70 times 10 negative 6 coulombs. We're trying to find the field strength right there at a distance of 0.022 meters away from it. What's the field strength at that point position P? Hey, this is a great question because it's pretty obvious, I think, here, whether we're dealing with a producer or experiencer. We're trying to find a field strength right there at point P. We don't even have something there to experience it, let alone know anything about it. We've got something over here which is clearly causing the field over here. Maybe, you know what, maybe there is something there to experience that field. If there is, we sure don't know anything about it. So we've got to use the producer equation here. E is equal to KQ over R squared. We're dropping the sign of the charge there. We always do, no matter what the equation is. We do the math, we get 3.16 times 10 to the 7. And the units for that would be newtons per coulomb as well. Hey, let's say we change this question around just a little bit and said, hey, there's a charge of 3.5 times 10 to the negative 8 coulombs at that point P. What would be the field experienced by that? Wouldn't change the question at all. The field that's produced by this guy is experienced by whatever it is that's there, if there's anything there. Listen, here's the rule of thumb. If you have a field, or you're looking for a field, at a certain point, then that point, if you've got the value of a charge where you're trying to find the field or where you have the field, then that charge is going to be an experiencer. If you have the value of the charge at a certain distance from the field, then that's going to be a producer. Right here, okay, we've got the charge a certain distance from the field. That's a producer. Back here, okay, we got the charge where we're trying to find the field. That's an experiencer. All right? Let's finish off these two questions now, page 549. And once you've done these two questions along with the other two we just did, that's it for today. You can take a look at those check and reflect questions that I sent earlier if you want and work on those for the rest of the class.